So we're going to talk about vectors and vectors in the plane. And we're starting off with the component form of the vector. So we need a couple of definitions to get started. The first is what a scalar is. So a scalar is just a number, and it tells magnitude or size, how big something is. And this is important when we talk about vectors because we always like to know about the magnitude. Now I'm going to give you the definition of a vector. So the special thing about a vector is it includes direction. So it has direction and magnitude. And we call it a directed line segment. And usually when you see it, it's either bold-faced or with an arrow on top. I use an arrow on top. So when I write a vector, this would be the vector v with an arrow on top. So then when we talk about vectors, we have to talk about where they are because they always have a direction and magnitude, and they can be equivalent in a lot of places, but we want to talk about standard position. So standard position is how we're really going to usually talk about our vectors and how we relate to them. That way we're all coming from the same place, and in this case, we have a vertex at the origin. So now we can get to our definition of the component form of a vector. So this is the definition of a component form of a vector on a plane. So I have a vector, and it's in the plane with initial point at the origin, and it has a terminating point at some point we're going to call v1, v2. So in the component form is written as this: v equals v1, v2. It's very important that you have these kind of brackets. These brackets indicate that it's a vector. If you have parentheses, it's not a vector, it's a point. So what we know is that if we have this component form, we know that v1, we call v1 and v2 the components, and we have one other special type of vector. We have a zero vector, and that's it looks like this, and that's when the component form is 0, 0. So it starts at 0 and ends at 0, and obviously its magnitude is also 0. When do I have equal vectors? Vectors are equal. So U would equal V only if U1 equals U2, equals V1, and U2 equals V2. They have to equal each other. If that's the case, then the vectors are equal. So each of the components equal each other. So my last definition here is the magnitude. And that's just to find we use these double bars, kind of like absolute value, but they're double bars. And it just equals the sum of the squares of the components, square root of that.